The concrete ring is still in the ground at Sydenham Hill, 1 metre thick, 3 metres wide, 18 metres in outside diameter, poured in Portland cement sometime between 1854 and 1856, one of the earliest structural applications of that material in the whole of Britain. The engineers who specified it had no long-term data to support their confidence. They used it anyway, because the alternative was another tower that fell down. Above this ring, for 85 years, stood one of 2 iron towers designed by Isambard Kingdom Brunel. Each was 284 feet tall. Each held a tank 38 feet deep and 47 feet across. Each tank, when full, contained 448,000 imperial gallons, approximately 2,000 tons of water, suspended above South London, at a height sufficient to drive fountain jets 250 feet into the sky. The towers were not decorative. They were hydraulic engines in the form of buildings, and they were asked to perform a task that had already defeated one set of engineers entirely. They did not fail. For 85 years they held. Neither tank leaked structurally, neither tower shifted, neither joint gave way under the sustained, relentless daily pressure of 2,000 tons of water pressing outward in every direction simultaneously. The towers no longer exist. They were demolished in 1941, but the foundation is still there. It has not moved. It did not need to. That is where this story begins. To understand why Brunel's towers held, you first need to understand what came before them, and why it didn't. When the Crystal Palace was relocated from Hyde Park to Sydenham Hill in 1852 and 1853, Joseph Paxton envisioned a water spectacle of extraordinary ambition. 12,000 fountain jets, main display columns reaching 250 feet, a system consuming roughly 120,000 gallons of water per minute at full operation. To achieve the necessary hydraulic pressure, the water had to be elevated, held in tanks above the level of the fountains, so that gravity could do the engineering work. The first towers were designed by Charles Hurd Wilde. They were built of brick. They were filled. Then they came down. The precise sequence of events is not extensively documented in surviving records, but the structural conclusion is not in dispute. Wilde's towers failed under the weight of water in the tanks. The company had promised Queen Victoria displays that would rival the fountains of Versailles. What they had instead was a very considerable quantity of collapsed brickwork, and an engineering vacancy that needed filling by someone considerably more capable. Brunel was consulted. He accepted. And he began from a fundamentally different premise than his predecessor, not what shape to build the towers, but what forces they would actually have to resist in every axis, at every joint, over every hour of every operating day, without exception. This was not restoration of a failed design. This was an interrogation of why the design had failed, followed by an answer in cast iron and Portland cement that has outlasted the building it was meant to serve by the better part of a century. Before we continue, a brief interruption, which is more than these towers had in 85 years of continuous operation. If you find value in documenting the things that were built to last, the decisions, the specifications, the engineering principles that made longevity possible, consider subscribing. And this channel exists because someone should be paying attention to these structures before the last people who understand them stop answering questions. And if you have worked on something like this, maintained it, repaired it, understood the load paths that kept it standing when everything around it failed, tell us in the comments. What was it? What held? What almost didn't? We are genuinely interested. Unlike most comment sections, this one occasionally contains useful information. Now, back to the towers. Brunel's first decision was the ground. Wilde's brick towers had failed because the loads they carried exceeded what their structure could transmit safely to the earth. Brunel resolved this at the very bottom. The foundation for each tower was a ring of Portland cement concrete, 1 metre thick, 3 metres wide, 18 meters across in outside diameter. Below it, the ring reached approximately 3 meters into the Sydenham subsoil. This was not a precaution. This was a calculated statement of intent about how much the structure above it was going to weigh, and how consistently it was going to weigh that much. Portland cement was a relatively recent material in 1854. Joseph Aspdin had patented it in 1824, and its structural applications were still being established at the time Brunel committed it to these foundations. The decision to use it here was deliberate. Portland cement sets harder than traditional hydraulic lime mortars and develops its compressive strength over time rather than declining. A foundation built of it would not degrade under sustained load. It would consolidate. On top of the concrete ring, the Brunel specified a drum of tapering brickwork 5.5 meters tall, laid in English bond. From this drum rose 12 cast-iron foundation plates, precisely positioned and precisely loaded, from which the iron columns of the tower structure climbed upward. The transition from earth to concrete to brick to iron was not a set of compromises. It was a load path, each material doing the thing it did best, in the order and proportion that made the assembly as a whole stronger than any single element could have been alone. Brunel had been building load paths since his 20s. He knew exactly what he was doing. Above the 12 foundation plates, the tower rose through 10 stories of cast-iron columns and bracing, clad in cast-iron panels around the circumference. Each tier was 20 feet high. The total height of the structure from ground to the balcony floor surrounding the tank was 200 feet. Above that, the tank itself added a further 84 feet. The columns were not structural decoration. They were precision castings produced by Fox, Henderson and Company, the same firm that had built and then reassembled the Crystal Palace itself, and which had previously constructed the roof over Birmingham New Street Station, then the widest railway roof in the world. They understood what cast iron could do under sustained compressive load, and they understood the tolerances required to make it do it reliably over decades rather than years. But Brunel was not satisfied with columns and cladding alone. He knew that a structure of this height and diameter, under the kind of lateral forces generated by wind and by the dynamic behavior of 2,000 tons of water shifting as it was drawn down and replenished, it would experience fatigue in ways that purely vertical load analysis would not predict. The columns needed bracing against horizontal displacement. They needed an element that would maintain the geometry of the whole structure under dynamic loading. His answer was the diaphragm. Each tower contained 10 horizontal diaphragms of wrought iron, each 5 feet wide and weighing approximately 6 tons. These were fixed between the columns and the connecting pieces at each tier, and tied together by iron rods 1 3/4 inches in diameter and 32 feet long. And the diaphragms did not merely brace the structure. They interconnected it, meaning that a force applied at any single point was distributed across the entire frame, rather than concentrated at one column or one joint. It is the difference between a chain and a net. Wilde had built a chain. Brunel built a net. The tank sat at the top of all this, 38 feet deep, 47 feet in diameter. Each one, when full, held 448,000 imperial gallons. The weight of that volume of water was approximately 2,000 tons per tower, pressing downward through the columns and diaphragms and foundation plates and brickwork drum and concrete ring into the Sydenham subsoil. This was not an intermittent load. The tanks were kept filled during operating periods. The structure held this weight continuously, for days and weeks and months and years on end. The tank itself was a cylindrical iron vessel under constant hydraulic pressure. The water inside pressed outward on the tank walls with a force proportional to the depth of water above each point, greatest at the bottom, where 38 feet of head was acting on the lowest courses of the tank structure. The joints between the cast-iron sections had to be made watertight against this pressure, not just at commissioning, but permanently, under conditions of thermal expansion, vibration from the wind, and the mechanical cycling of the tank being drawn down and refilled. Brunel's approach to the tank joints was methodical. The sections were precision cast, the machining tolerances on the mating faces kept tight enough that the caulking applied to each joint had controlled, consistent depth to work in. A caulked joint in cast iron is only as reliable as the consistency of the gap it is filling. Vary the gap, and you vary the compression of the caulking material. Vary that, and you create differential sealing. Create differential sealing, and you create the conditions for a slow leak to develop under sustained pressure, the joints held, and all of them, for the entire operational life of the towers. Brunel had specified what his predecessors had assumed. That was the difference. The towers were assembled from components produced in different workshops, transported to Sydenham Hill, and erected in sequence by a workforce working to drawings and fit-up specifications they had never seen applied at this scale before. For this to work, for every column section to mate correctly with the next, for every bolt to fit every nut, for the diaphragm connections to take their specified loads without adjustment or shimming in the field, the individual components had to be made to standards that existed independently of the men making them. Yeah, that standard was the British Standard Whitworth thread. Joseph Whitworth had published his proposals for a standardized screw thread in 1841, 15 years before these towers were completed. The thread form he specified, a defined angle, a defined pitch for each diameter, and a defined radius at the root and crest of each thread. Before Whitworth, every workshop cut threads to its own practice. A bolt made in Manchester and a nut made in Birmingham did not necessarily fit. After Whitworth, they did, if both workshops observed the standard. A recent analysis of surviving fasteners from the Crystal Palace site, including bolts and nuts recovered from the water tower base during excavation work in the 1980s and after, has confirmed that the components were manufactured to British Standard Whitworth dimensions. This was not incidental. It was structural. The ability to replace a lost or failed fastener with one made to the same specification, without sending back to the original manufacturer for a pattern part, was engineered into the design from the outset. The towers were made of iron, but they were held together by standardization. And Whitworth's thread meant that the structure's integrity was not hostage to any single supplier or any single workshop. That is a maintenance decision dressed as a fastener specification. The accountant who asked why standard threads cost more than bespoke ones did not work there long. The towers became operational on the 2nd of June, 1856. The fountains were turned on 16 days later, on the 18th of June, in the presence of Queen Victoria. The main jets reached 250 feet. A gust of wind swept the spray over the royal carriage. The Queen got wet. The towers had performed precisely as specified. This was considered a success. The company's ambition had been to rival Versailles. In the matter of fountain height and volume, it had exceeded it. What Paxton had imagined, Brunel had made structurally possible. The tanks had filled, the pressure had built, the valves had opened, the joints had held. 2,000 tons of water, elevated above South London, had passed through the system and produced exactly the effect required, without incident. Brunel's towers had been operational for less than 3 weeks, when they demonstrated that the entire engineering premise was sound. They would go on demonstrating it for the next 80 years. Brunel himself died 3 years later, in 1859, at the age of 53, and the towers were among his last major engineering commissions. He did not live to see them in their full operational maturity. He had, however, designed them to work without him, which was, in the end, the highest form of engineering compliment he could pay to anyone, including himself. The towers would outlive the Crystal Palace Company, and the era that built them. By the time anyone thought seriously about dismantling them, they had already survived everything else. The towers outlived their function. By 1930, the water features at Crystal Palace were no longer in operation. The tanks that Brunel had engineered to hold 2,000 tons at sustained pressure sat empty. The towers continued to stand. In 1872, the lower 3 floors of the South Tower had been converted into a lecture room, a drawing office, and workshops for the Crystal Palace School of Practical Engineering, one of the earliest technical colleges of its kind in Britain. The tower that had been engineered to resist dynamic hydraulic loads now supported the education of engineers. And this seemed appropriate. It relocated in 1916. The tower continued to stand. From July 1933, John Logie Baird and Baird Television Limited used the South Tower for experimental television transmissions. The only British television broadcasts available from September 1935 until the BBC began transmitting from Alexandra Palace in November 1936. Brunel's hydraulic tower became a television mast. This was not what it had been designed for. It managed it without difficulty. On the 30th of November, 1936, a fire broke out at the Crystal Palace. 88 fire engines attended. The palace was destroyed within hours. The blaze was visible from the Sussex Downs. The 2 water towers survived it. The firemen's principal success that night was saving the South Tower, around whose base the fire burned, and whose integrity, had it failed, would have threatened the houses of Sydenham Hill directly adjacent. It did not fail. It had been engineered not to. The North Tower was demolished with explosives in 1941. The South Tower was taken down floor by floor. The reason given was that they could have served as navigation landmarks for Luftwaffe bombing raids on London. That may be true. It is also true that by 1941 they had been standing for 85 years through 1 major fire and 1 global war, without a joint failing and without a tank leaking. They were not taken down because they were inadequate. They were taken down because they had become inconvenient. The concrete ring is still in the ground at Sydenham Hill, listed at Grade 2 by Historic England, identified as one of the last major commissions of the foremost engineer of the Victorian age, and as evidence of the earliest structural use of Portland cement concrete in British engineering. The base was excavated and recovered in the mid-1980s. It is adjacent to the Crystal Palace Museum, which occupies the former School of Practical Engineering that Brunel's South Tower once housed. The ring has not moved. It has not cracked under the weight of what stood above it. It has not dissolved. But the Portland cement that Brunel's engineers specified, without long-term data to support their choice, on the basis of engineering judgment alone, has simply continued to exist, doing what it was made to do, which is hold its position under load. The tanks held 2,000 tons. The towers held the tanks. The foundation held the towers. The ground held the foundation. Brunel designed every link in that chain of transmission. He designed none of them to be the weakest. And that is the question this channel keeps returning to. Not whether these things were remarkable, they were, demonstrably, but why that kind of design discipline has become the exception rather than the rule. Why the engineering of load paths, of standardized fasteners that any competent workshop could reproduce, of joints specified to tolerances tight enough that caulking would work correctly for decades, now constitutes a kind of archaeological discovery rather than a baseline expectation. The towers were taken down. The foundation remains. It was built to last, and it has, and it will continue to do so, long after the people who demolished the towers above it have been forgotten. This was not a museum piece. It was not meant to be preserved. It was meant to work. It did. If this subject interests you, and we suspect it does, since you are still here, subscribe to the channel. There are more structures, more decisions made by engineers in the mid-19th century that are still paying off today, are largely unnoticed by everyone, except the few people who know where to look. And if you have a connection to what we have just described, a family member who worked on a structure like this, an engineering site you know that contains something built to last and left to be forgotten, tell us in the comments. The knowledge of how these things were built and why they held was never formally written down in a form anyone thought to preserve. It lives in the ground at Sydenham Hill, and in the people who bother to look.